popular circuit made by Eric Taylor, which is also similar to the one that Richie Burnett showed people a long time ago. So, I mean, the general concept is pretty simple. Somehow you derive a gate drive, and then from there, you're just trying to tune this load network and shaping the drain waveform to get good switching. So this is essentially the same setup. You've got your RF choke, then you've got your DC blocking here, then you've got a drain source shaping capacitor here, that's the shunt, and of course this becomes your primary. The only difference is, of course, right here, so you got a crystal stage, and then you're basically just creating an RF drive stage for some main final switch. In this case, this would be the final stage. You got multiple stages building up to driving this switch here. And it's like, all right, well, I'm just going to use a beefy ass gate driver, right? So that's really the only difference, right? So I really don't end up with a sinusoidal drive here. It's basically a fairly stiff square drive, right? All right, so this guy, just right now with the drain not loaded and powered, it's just the basically the current draw, power draw of just driving the gate. And that's the gate waveform. So for one, you can see it's a pretty high duty cycle. It's well over 50%. It's not like 60 or anything, but 56 is pretty high. If I wanted to, I guess I could try to trim around and play with adjusting that on time on the hex inverter. The other option would be inverting using another output and trying to go for, I guess, like 44%. But I think I'm better off sticking with the 56. So what I might do is just try to tune this like that. Part of the thing is I'm using this 30 amp peak gate driver. And I had like a bunch of these I bought a while ago, so I figured I would just use it. And part of the benefit there is, I get these pretty stiff edges right there. That's even with 5 ohms. But the problem is that particular chip has an under voltage lockout at 12.5 volts, right? So that means I can't drop my gate voltage down to only about 12 to reduce that power like I've had in some other ones. So I'm just running closer to 15, which is actually basically the test parameters for this particular FET, which can run 15 volts and 0 volts on the gate. This waveform is not perfect. It's actually a little bit dirty on top. You can see there's like the slightest little bit of jitter in it. It's not rock solid. So obviously a big part of that is just the fast switching here. Of course, I've tried to put it on this double-sided copper-clad board like this, and I'm actually using the Kelvin emitter on this one. So this one's the 4-pin. I'm using the Schmitt trigger oscillator. That's just because I don't have a crystal or anything. So I kind of want to see how it works. I know that it's worked before in the past, right? But I'm trying to go closer for like a true Class E setup with this one. So I don't know. But for example, that would be why, obviously, if you want a much more rock solid stable frequency, you probably want to use a crystal or something, right? This is not going to be super stable. So the problem with using this approach, I'm using this 15 volt regulator. Technically, the average power, it can push what would be necessary to drive a SIC gate, no problem, right? But this frequency, it's pushing high peak current pulses. It's pushing those pretty fast edges. So the only real solution I've ever had in the past trying to use this simple setup is just trying to decouple the crap out of it, right? What's helping the most is more like adding something like 10 microfarad caps, as many as I could get damn near. So I've got about 30 microfarad here, which did help quite a bit, but I've also tried to add a little bit right directly on the pins as close as I could get them, right? So by trying to decouple that as best as I can, I could try to keep that high frequency loop over here and a little bit away from the regulator, right? I didn't really think about this board. I kind of went, carved it as I went, and realized it wasn't the best approach. But anyway, you can kind of see like that's kind of how this is set up. So all right, so here's how I've kind of got it set up. Wish I could spend more time on this. I really can't waste a whole lot of time, with the concept being I'm just going to throw a beefy gate driver on there. I'll say the end result was I modified the oscillator a little bit, used a much larger cap around the 1 nanofarad region. That keeps this from drifting around so much, especially when the field interacts with it. So it's not super rock solid, but it's a whole lot more stable than it was just by changing that. With this particular setup with these values, the coupling was like super crucial. It's always crucial. Even the slightest tiny little adjustments make a huge difference in the power. If you don't mount this thing properly to where it's not going to move around, you might nudge the primary. You see how easy it is to nudge that? You might nudge it somewhere and not realize, and now your tuning is all, it appears different than it was. You might start changing other values around unnecessarily, right? I don't really feel like playing around with that forever, so basically the compromise I ended up with, I kind of added a little intentional leakage right here with this little inductor coming off the drain. That's basically just in series with the primary. Ended up widening the primary diameter. I think I'm probably going to leave it about like that. I might change it a little bit, but got my compromise about like 30 volts or so. We'll get that going. Cut that on. So I got it at about 30 volts. It's pulling like 130 watts or something like that. And that's what the switching looks like. So I've got a little bit of margin to cut it up a little bit more. But yeah, this is probably where I would typically run it at. So about 130 watts, 4 amps. So that kind of keeps it in the that keeps it in the region where I could run it from like one of my battery supplies or something, or like even that guy. Although if I run it off this, I could still crank it up. The problem is, if I turn it up too high, it's going to start hard switching. So yeah, I could pull some pretty good power off that thing, but it's going to start heating the FET up. Whereas I could run it like this for a very long time. It's not going to get warm. But for example, see if when I pull an arc off of it like this, see it start switching real hard. That's like I say, like with this particular type of topology, you know, I'm probably not doing it right for one, but it just seems like it's a whole lot harder to get this tuning set up to where you've got a relatively, let's just say a relatively large window of forgiveness. So whereas, you know, like I say, the Steve Ward style where you're pretty much just adding a shunt cap, you know, basically low side switching a primary, it just seems like, you know, I could tune it so when I draw a load like that or draw an arc from it, it doesn't change the switching relationship a whole lot. But I guess the whole way that this works is inherently different. It's kind of cool, right? You know, it doesn't take a whole lot. It's you're really just adding aside from the shunt, this series capacitance here. That's more or less about it, but yeah, not bad. Say it does put out a pretty good field, I'll tell you that. So it's like a black light right here. But yeah, I'll say I don't like that compromise to where, yeah, I might not be pulling arcs from it all the time. I'll probably be running it like this the majority of the time. Other thing, I can hear little kind of random artifacts coming in. That might be part of just the way that I've got this thing set up with the Schmitt trigger oscillator. But yeah, again, you can see it's not hard to detune. See how that detuning works. Doesn't really change the switching a whole lot. It's general phase relation. It's about maintained. It's kind of interesting because it does have to be loaded right. But of course, let's just say, well, let me bring it down. I'll bring it to like 12 or something, right? So that's what it looks like. It pulls about 50 watts. Nothing real impressive there. I mean, obviously, it still puts out a pretty good field. But if I wanted to hard switch it, I guess just say, at least with this particular tuning, you can see as I get up high, so there you go, about 60 right there. So I'm hard switching. You know, it's not switching as hard as it, I guess, possibly could be, right? But it's definitely nothing close to Class E right now. And, you know, it's got about half the damn drain voltage on it while it's cutting back on. So about 250, something like that. But I'll tell you what, the size of that flame with this topology running about that voltage is not bad. Where I think other similar builds to get about the same flame, I think I was probably pushing like 300, 350 watts maybe. So yeah, not bad. Like I say, I guess it's a decent trade-off. Like I say, I don't know. It might not be that way when tuning this thing to run from mains. I really don't like the mains. I don't want to have to smooth all the hum out. I'd rather just have a fairly quiet bush where, you know, at 2.7 and the little artifacts I can hear just from whatever's going on in this network here, I can hear a little something that's not quite as quiet as some of these other ones that I've made, but it's still pretty sweet. Yeah, it's not a bad flame. But I'm not sure if I would ever want to try to, like, let's just say I run it like about 40 right there is probably as high as I'd want to go, right? That still probably switches to the point where I could run it for a super long time. That heatsink's not very big, but it'll probably keep that heatsink from getting super hot. But you know, when I start cranking it up higher than that, it's definitely heating up with that hard switching, of course. So yeah, it's pretty cool. Secondary gets pretty damn hot along with the primary. Heatsink for the switch is still pretty cool. Well, I'm not going to say it's cold. I could feel some warmth on it. All that warmth I feel on it, which is not a whole lot, but that was from that short bit of hard switching I was doing. So I definitely couldn't run it like that for a super long period. But yeah, that's so right now it's just a little under 2.7 after I've readjusted the oscillator, the gate waveform. So that's kind of what I've tried to make work with that 50% or 56% duty cycle, right?